Hello everyone. This is our lecture on section 1.3, vectors and vector equations. So, definition. Given an integer n bigger than or equal to 2, okay, a vector v is, in n-dimensional space is a column of n components, each of which is a real number, typically. So v, and usually we write vectors with a little hat on them like that. In the book, they probably use the notation. Let me see. Yes. In the book, they would use the notation like a bold-faced V. So, it would be like this for a vector. But, in handwritten notes, or sometimes in typed notes as well, a vector V is written, as the V, and they put a little hat on it. So it's just like this: A1, A2, AN. Right? In calculus, vectors are written like this. If you've taken Calc 3 already, or if you haven't taken Calc 3, don't worry about it. Like a three-dimensional vector would be written like that, as a row rather than as a column. And that just depends on context, okay, which one it is. In linear algebra, typically it's more convenient when you're dealing with the type of linear algebra that we're going to be doing here. It's more convenient to work with columns rather than rows. But, whatever you read, the context will be clear. So here they're always going to be columns. Vectors are columns. So in 2 dimensions, in the xy plane, if you have a point A, B here, and a point X, Y over here, then the vector whose head, so the vector the vector is a line segment from this point to that with a direction. So one point is the head, and the other point is the tail. Right, so the vector v in this case, so geometrically it looks like this, and the vector v in this case is head component minus tail component, head minus tail. Okay, so for example, the vector equal to, we'll say 2, 1, like that. So there's lots of different vectors 2, 1 that you can find here. So if this is the point 0, 0, and this is the point 2, 1, then the vector v is between those 2 points. But it's also between other points like that. So if this is the point 0, 3, it's also right there. And this is going to be the point where the head minus the tail is 0, 3. So what's that going to be? Right, it's going to be 2, 4. or wherever else you might be. Okay, whatever else your head and your tail might be, these are all the vector v. In 3 dimensions, okay, how do we see vectors as 3 dimensions? In 3 dimensions. So in 3 dimensions, you have 3 coordinate axes, x-axis, y-axis, and a z-axis, like that. Right, so x and y-axis are flat on the paper, and the x-axis is coming out, from the paper towards you. So it's kind of drawn as a slanted line. So this is a perspective drawing. So if this is the origin, x, y, and z all equal to 0, and then you had a vector you wanted to see, so say the vector with x coordinate 1, vector with y coordinate 2, and z coordinate 3, you would have this box here. And the vector would go from the origin to this point. And this point right here has coordinates, x equal to 1, y equal to 2, z equal to 3. So this is the point 0, 0, 0. This is the point 1, 2, 3. And this vector right here is the vector 1, 2, 3. Let me draw it over here. Okay. In dimensions higher than 3, typically we don't draw vectors sitting in space because it's very difficult to visualize vectors in higher dimensions. Typically, well, depends what subject you're looking at, but it's going up to 4 dimensions is is definitely a stretch of the mind. Going into higher than that, well, that becomes even worse. Okay, so those are vectors, and there's several algebraic operations that we do with vectors. So we've defined a vector quantity. A scalar quantity is just a real number. And scalar multiplication of a scalar k and a vector v is defined as follows. So if you have your scalar k and vector v, you write the scalar on the left and the vector v on the right. So this is k, and then the vector v, say it looks like this, a1, a2, up to an. That becomes the vector ka1, ka2, kan, like so. Geometrically, multiplying v by k stretches, k bigger than 0, stretches v's length by a factor of k. multiplying v by k less than 0 does the same and reverses its direction. So the picture would look like this. If this is vector v, then vector minus v would be this. All right, so multiplying by a negative stretches by a factor of the absolute value of that scalar k, but that's just a -1, so it's got the exact same length, and reverses the direction. So that's v, that's negative v, this would be, say, 1/2 v, and this would be 2v. So on and so forth. So v twice v is the same direction, but twice the length. Half v, same direction, half the length. Negative v, same length, opposite direction. Okay, so that's operation number 1, algebraic operation number 1 with vectors. It's called scalar multiplication. And then there's another operation called vector addition. Given vectors u equal to a1, a2, an, and v equal to b1, b2, bn, like that. So they have to be vectors of the same size. So both two-dimensional, both three-dimensional, both four-dimensional, so on and so forth. Define u plus v equal to the vector that we just add the components, a1 plus b1, a2 plus b2, an plus bn. Okay, so geometrically, u plus v is the diagonal of a parallelogram defined by u and v. So the picture that you should have in your head, so if that's vector u, and this is vector v, right here, say, and you put them both with the same tail. Okay, as I was saying before, you can always take a vector and give it a different tail. So as long as head minus tail is the same vector, then they're the same vector. So instead of putting the tail of v, instead of putting the tail of v at the tail of u, you could also put it at the head of u. And instead of putting the tail of u at the tail of v, you can put it at the head of v. So I could put it up here. So u and v, whoops, didn't work out. Try that again. There we go. So u and v form a parallelogram in this fashion here. All right, so this is vector v, with this head, this tail, and this is also vector v with a different head and a different tail. But they're parallel because they have the same direction. This is vector u, this is vector u. So they form a parallelogram. And then u plus v, nicely enough, is the diagonal of that parallelogram from the common tail to the common head. U plus v. All right, so if you draw u and v tip to tail like this, head to tail, so head u, tail v, then u, v, and u plus v make this nice triangle. Or you can do v plus u, right, with tail of v and the tail of u with the head of v, and then you form a triangle this way. So u, v, and u plus v make a triangle like this. So notice from the diagram, also implies that u plus v is equal to v plus u, because it's either the third side of this triangle or it's the third side of that triangle. Right? This triangle being u plus v, this triangle being v plus u. The other diagonal of the parallelogram, well, what's that going to be? Let me see if I can put it on the same page. So what about that diagonal of the parallelogram? Which vector is this? Right, I mean, if I call this vector x, and call that vector x, then u plus x equals v. Right, u plus x equals v. Therefore, x is equal to v minus u. Yeah? So the other diagonal of the parallelogram is v minus u, or u minus v, depending on which direction it is. On which direction is chosen. For the diagonal. Alright, so in this case, the diagonal is v minus u. Right, because u plus v minus u is v. If you want to go in the other direction, then v plus u minus v should be equal to u. Alright, so this direction is v minus u, the other direction is the negative of that, u minus v. Alright, also the zero vector in n dimensions is the vector where every component is 0. Okay, so these are the real numbers 0, and this is the vector 0. So the 0 vector in n dimensions is that. Okay? some properties of addition and scalar multiplication of vectors. Vector addition and scalar multiplication are as follows. Well, one, like we were talking about before, vector addition is commutative. It's also associative. U plus V plus W is U plus V plus W added first. So, the same thing with the same sort of things with addition, ordinary addition of real numbers. They carry through with vector addition. There's a few other properties. U plus, if you take the scalar multiple of U with -1, that's equal to the 0 vector, right? Where by -1 times U, we mean the negative of U. Okay. So maybe I could write it like this. So U minus U is 0, where minus U is -1 times U. The scalar k times the vector sum U plus V is equal to KU plus KV. So you've got this kind of distribution property where scalar multiple distributes over vector addition. By the way, notice that, with this multiplication, so we have two operations so far with vectors. We've got addition of vectors and scalar multiplication of vectors. That's it. We don't have anything else yet. We will have something else later on. In particular, we don't have a way of multiplying vectors. Okay, when you talk about how to multiply vectors, there's actually, that's opening up a big topic that we'll touch on later in the course. Well, towards the end, actually. So there's not one way to multiply two vectors together. There's lots of different ways. If you've taken Calc 3, you saw two already, right? There was the dot product and the cross product. So, we'll talk about that later anyway. There's definitely, that's definitely a big subject. 5, there's another type of distribution. If you took a sum of two scalars and multiplied by a vector v, then that's scalar SV plus scalar KV. You also have this kind of, I guess S and K. Scalar S times vector KV is equal to scalar SK times vector V. And, the number 1 times vector V is going to be just equal to vector V, of course. All right, so just some algebraic properties. They're all expected properties, but, there they are. We spelled them out specifically. All right. Linear combinations. Given vectors v1, v2, vm, all in n dimensions. Okay, so given these vectors, a linear combination of v1, v2, Vm is of the form okay, so you have scalars k1 v1 k2 times v2, and you add all that up. So a linear combination of these vectors, essentially it's a sum of these vectors. The sum of multiples of those vectors. Does that sound familiar at all? A sum of multiples of vectors? Did we do that already in section 1.2? Well, sort of. I mean, we've defined vectors as columns of real numbers. Sometimes you might think of vectors as rows of real numbers. And one of our elementary row operations from section 1.1 and 1.2 was to take one row and add to it or subtract from it a multiple of another row. So you take two rows, multiples of two rows, and you add them together. All right, so that was a linear combination of two vectors. All right, so this is more generally a linear combination of n vectors. This is v1. All right. So it's another. This is another. Really central concept in linear algebra is a linear combination of vectors. Okay. So for example, 3 times the vector 1, 1, 0 plus half times the vector 1, 5, negative 2 minus 6 times the vector negative 1, negative 1, 0. Or negative 1, negative 1, 1, we'll say. Okay, what's that going to be equal to? So first you do the scalar multiplication, 3, 3, 0, plus half, 5 halves, minus 1, plus 6, 6, minus 6. Right? And that's going to be equal to 3 plus 1 half plus 6. So that's 9 and a half. Right? So that's 19 halves. 9 and a half. 9 plus 5 halves. Right? So 5 halves is 2 and a half. So it's 11 and a half. So 23 over 2. And then 0 minus 1 minus 6 is minus 7. Right? All right. So that's a linear combination. Did I get the arithmetic right? 9 plus 5 halves, it's 2 and a half, 11 and a half. 11 and a half, so it's 22, 23, right, 18, 19. All right. Question. Can we find scalars such as, or so that, we can express, can we find scalars to express vector 1, 5, 1 as a linear combination of vectors 3, minus 1, 0, 1, 2, 1, 1, 0, 1. All right. Can we find scalars to express this vector 1, 5, 1 as a linear combination of these three vectors? Okay. So let x1, x2, x3 denote scalars, such scalars if they exist. Okay, so, well, let's try to answer that question. We want to express 151 as a linear combination of these three guys with three scalars, which are unknown at this point. Unknown, we don't even know if they exist. Right, so find x1, x2, x3 such that x1 times 3 minus 1, 0, plus x2 times 1, 2, 1, plus x3 times 1, 0, 1 is equal to 1, 5, 1. Right? This is a linear combination of those three vectors, and this is the result that we would like to have, 1, 5, 1. Is 1, 5, 1 a linear combination of this vector, and this vector? Okay, well, what does this boil down to? Well, let's evaluate this linear combination on the left. So first we multiply through the scalar. So this is 3x1 minus x1, 0, plus x2, 2x2, x2, plus x3, 0, x3, equal to 1, 5, 1. So again, we want to determine scalars x1, x2, and x3 such that this sum is equal to 1, 5, 1. Well, what is this sum? Let's evaluate. It's 3x1 plus x2 plus x3 in the first component, minus x1 plus 2x2 plus 0, x3, and then on the bottom it's x2 plus x3. So these three vectors sum to this vector, and you want that vector to be equal to 1, 5, 1. Right? For these two vectors to be equal, we need scalars x1, x2, and x3 to satisfy the following system of equations. Three x1 plus x2 plus x3 equal to 1. Minus x1 plus 2x2 plus 0x3 equal to 5. And then x2 plus x3 equal to 1. Right, so there's our old friend from sections 1.1 and 1.2. So we have restated or given another meaning to what a system of linear equations is. A system of so many linear equations with so many unknowns. It can be thought of as a question about linear combinations. Can we find scalars to express vector 1, 5, 1 as a linear combination of vectors 3, negative 1, 0, 1, 2, 1, 1, 0, 1? So this question is the same question as asking, is there a solution to this system of equations? Here's 1, 5, 1, 1, 0, 1, 1, 2, 1, 3, negative 1, 0. Is this, is this consistent? Is this system consistent? Does it have a solution? Well, let's check it out. So there's our system of equations. So let's write it with this matrix form. So the matrix is 3, 1, 1, 1, minus 1, 2, 0, 5, 0, 1, 1, 1. So now we're going to do our elementary row operations to get this guy down into row echelon or reduced row echelon form. So this column, I want to move row 3 to row 2. So row 3 is going to get moved to row 2. And I want to move row 1 up to, I want to switch row 2 and row 1 as well. So it's going to give me minus 1, 2, 0, 5, 0, 1, 1, 1, minus 1, no, not that one, 3, 1, 1, 1. So actually, no, I took row, I'm not switching row 2 and row 3. I'm switching row 1 and row 3. And then I'm switching row 1 and row 2. Okay? Now I want to multiply row 1 by negative 1 to make this a positive 1. So that's going to give me 1 minus 2, 0 minus 5, 0, 1, 1, 1, 3, 1, 1, 1. And now I'm going to do row 3 minus 3, row 1. Right? Row 3 minus 3, row 1. Multiply this one by 3 and subtract it from that. So we're just changing, again, we're just changing row 3. We're not changing row 1. So 3 minus 3 is 0. 1 plus 6 is 7. 1 plus 0 is 1. And 1 plus 15 is 16. And now I'm going to subtract 7 of row 2 from row 1, or row 3. So row 3 minus 7, row 2, in order to get a 0 there. So first row stays the same. 0, 1, 1, 1. 0, right? So 0 minus 0 is 0. 7 minus 7 is 0. 1 minus 7 is minus 6. 16 minus 7. 16 minus 7 is 9. Okay. Multiply row 3 by negative 1/6. And it's going to give me 1 minus 2, 0 minus 5. 0, 1, 1, 1. 0, 0, 1. And then 9 over 6 is 3/2. All right. Now I'm going to subtract row 3 from row 2. So row 2 minus row 3. So so now we're in echelon form, right? That's the matrix in echelon form because the leading ones in each row, or the leading coefficients, the leading non-zero term in each row, they go strictly down to the right. As you go down, they move strictly to the right. Now I want to get in reduced row echelon form so that every column has every column with a leading coefficient is going to have exactly one non-zero in that row. All right, so this is 1, 0, 0. This is okay. Now I want to get a 0 here and a 0 here, and this one's already 0. So I want to make all this 0. So you have to start with subtracting row 3 from row 2, leaving row 1 alone at the moment. So 0, so 1 minus 0 is 1. 1 minus 1 is 0. And then 1 minus 3 halves, 1 minus 3 halves is 1 plus 3 halves, which is 5 halves. And then I've got 0, 0, 1 minus 3 halves. Almost there. Add row 2 twice to row 1. So row 1 plus 2 row 2. Notice, by the way, we couldn't do this step previous to this step. If I added row 2 twice to row 1, what happens? This component here, that coefficient, which was a 0, will suddenly be non-zero, right? This will become 0 and that'll become 2. That's not what we want. We want to leave this as a 0. So we got to make this guy 0 first. Okay, so we add 2 here. So 0 plus 1 plus 0 is still 1. And then minus 2 plus 2 is 0. 0 plus 0 is 0. And then minus 5 halves. Minus 5 halves plus 2 times 5 halves is 0. 0, 1, 0, 5 halves. 0, 0, 1, minus 3 halves. So now we've got this matrix in reduced row echelon form, and we get that x1 is equal to 0, x2 is equal to 5 halves, and x3 is equal to minus 3 halves. So that is the unique solution for scalars x1, x2, x3. Let's check. All right, so my original vector equation, where was it? That initial linear combination, right here. See? Right there. All right, so here this is. Let us replace these scalars. Well, actually, let's leave it as x1 for the moment. And now we'll replace. There we go. So it was 0, 5 halves minus 3 halves. 0, 5 halves minus 3 halves. Okay, so this becomes 0, 0, 0. Plus this one becomes 5 halves, 5, 5 halves. Plus this becomes minus 3 halves. 0 minus 3 halves equal to 1, 5, 1. Add these together. 0 plus 5 halves minus 3 halves is 2 halves, which is 1. 5 plus 0 is 5. 5 halves minus 3 halves is 1. So 1, 5, 1 equals 1, 5, 1. All right, all checks out. Okay. So just to quickly summarize again, so to summarize, asking the question, is vector B a linear combination of vectors v1, v2 up to vm is the same as asking the question, is the system of equations given by the coefficient matrix V1, so first column is V1, second column is V2, last column is Vm, and then you have this little dotted line here for the equals, and then you have vector B there. Is the system of equations given by coefficient matrix this consistent? Okay, they're the same question. The answer is yes to both or no to both. Okay, they're equivalent questions. All right, so now we've talked about linear combinations. We've given a definition to linear combinations. So here's another important concept with linear combinations, and that's called spans. Okay, given vectors v1, v2 up to vm, span v1, v2 up to vm is the set of all possible linear combinations of v1 to vn. Okay, all possible linear combinations. So, for example, span of, and let's do some four-dimensional vectors for this example. 1, minus 1, 1, 0. 3, 0, 2, 2. 1, 1, minus 1, 2. So the span of these three vectors contains, infinitely many different linear combinations, right? Because those coefficients, x1, x2, x3, those scalars that you pick, they can be any real numbers that you like, so there's infinitely many possible choices. So it contains infinitely many different linear combinations. Here are some of them. So I could do 1 minus 1. So let's do this. Let me rate those guys first. Let's copy. And let's pick some coefficients and just calculate. Well, I could do 0 plus 0 plus 0, right? And that's going to add up to what? That's just going to be the 0 vector, right? So the 0 vector is always going to be in the span of a bunch of vectors. I've got this span of several vectors, these 3 vectors or any other vectors. So notice that the 0 vector is always going to be in the span because you can always pick scalars 0, 0, 0, 0, 0. All right. How about this? Let's do 1 of these plus 2 of these minus 3 of these. All right, so 1 plus 6 is 7, minus 3 is 4. Minus 1 plus 0 minus 3 is minus 4. 1 plus 4 is 5, plus 4 is 9. And then 0 plus 4 minus 6 is minus 2. Right, so that linear combination has that sum. Of course, you can have non-integer scalars. 1/2 minus 1 of these plus, I don't know, half again is going to be equal to, so that's 1/2 plus 1/2 minus 3, so that's minus 2. Minus 1/2 plus 1/2 is 0 plus 0. 1/2 minus 1/2 is 0 minus 2. And then 0 minus 2 is minus 2 plus 1/2 of 2 is 1. So you get minus 1. So on and so forth. So there's 3 vectors in the span. And of course, there's going to be infinitely many vectors in the span of a set of vectors that are chosen, including just one vector. So now let me ask you a question. Is vector 1, 5, 1 in the span of vectors 3, minus 1, 0, 1, 2, 1, and 1, 0, 1? Did we answer this question already? Did we answer this question already? Well, what is this asking? This question is just asking is 1, 5, 1 a linear combination of vectors 3, minus 1, 0, 1, 2, 1, and 1, 0, 1, right? This set here, span of these vectors, is the set of all linear combinations of these vectors. So I'm asking, is 1, 5, 1 in the set of all linear combinations? In other words, is 1, 5, 1 one particular linear combination of these guys? Right? But we already answered that question. This question, and the answer is yes. right? Where's that linear combination? It's back up here somewhere. Here it is. All right, 1, 5, 1 is a linear combination of these three vectors with coefficients, with scalars, 0, 5 halves, and minus 3 halves. Okay? All right. So that is the end of the lecture on this section. Is there one of the things I want to say? That's fine. Okay. All right. That's the end for section 1.3.